How are we going? My name is Jesse. I am a tutor in Melbourne and I also make GAMSAT videos. I make a whole bunch of different free content in preparation for the GAMSAT across mostly Section 2 and Section 3. Section 1 I kind of suck at. Today what we're going to be doing is going through set 14 of my sample Section 3 walkthrough videos. These are videos where I make a bunch of free questions that hopefully emulate something similar to the actual ACER exam. I try to draw on my experience as a tutor, as an educator, someone who writes a lot of questions, to hopefully write questions that are similar in style to what we're seeing in the actual test. I make them freely available so that you can work through them at your own pace, and these videos act as kind of worked solution videos for them as well. Hopefully you can take from it a few different tips and tricks on how I might approach questions. I try to explain as much as possible about the structure of how I've actually written them as well. And along that, there might be some points of theory that are useful too if you haven't already seen my crash course videos. If you're looking for the resources page, I realize I kind of sometimes assume that we've got the same people watching these videos as we're watching about 6 months ago. So if you're new here, you can find the resources page of mine in the video description below. I also link it on the About page on the channel as well. I probably need to actually link it to my actual website as well. I've never actually done that. I never think to do it. So yeah, if you're having any trouble finding it, it's just there. It's basically a Notion page turned into a website. So if you use Notion, then you should be very familiar with it. I'll try to keep this simple though. Basically, this set looks at a lot of data analysis and then some organic chemistry. I try to theme them and I rate them based on difficulty. I've put this one, I think, in the easy/medium basket. On my page, you'll see the ratings are actually all on there as well, so you can kind of work through them from easy to more difficult if you're trying to ramp up your study bit by bit. And yeah, we'll take it from there. So let's just dive right into it, I think. So first of all, we've got here this particular sample. Now, I have grabbed the data from a research study, but I've kind of extrapolated it and turned it into something different. If you're interested in learning about the research, I always link them in the video descriptions. I will probably link them on the resources page as well under it if you wanted to go and research the original one. This one's very specific though. It's about increasing or testing for meat quality in red meat in a very specific type of bull. And basing that red meat quality on the fatty acid profile. So if that is something that absolutely interests you, then you can read ahead a little bit further. But I've written the STEM myself around this, and I really just use the data to look at how kind of raw research can be extrapolated into a GAMSAT STEM. So we've got red meat is a common source of dietary protein. Meat quality can be measured by its compositional breakdown into different macronutrient groups, and evidence might suggest that the relative quality of meat sourced from cattle may be impacted by the dietary source of protein for the cow or the bull. So already we're starting to get a bit of a sense of what this STEM is going to be about. It's going to be about the impact of dietary source of protein on meat quality, measured by a bunch of different macronutrients. We don't yet know what that is. Then it says a study into the effects of dietary protein sources on meat quality in young Marchajana bulls. I have no idea if I'm saying that right. I'm not going to say it again and embarrass myself. Terrible at pronouncing words that I'm not familiar with. But it sounds Spanish. Maybe I'm just thinking of running of the bulls. But anyway, was conducted in which the young bulls were fed one of three diets: the fava bean diet, FB, soya bean diet, SB, as the protein-based diets, or a high caloric diet, the high energy diet. So I would probably, in terms of my note-taking, I'd probably be noting these down. Let's change the color here. So I'd be putting down, all right, so protein-based diets, and we've got the fava bean and the soybean. I wouldn't necessarily put a huge amount. I would just put fava, and then this one here, I'm just going to put soy or soya if you want to be fancy about it. And then the high energy, I'm going to put that one separately because it seems to be disconnected in the STEM there. High energy is, I'm just going to put energy on that one, and I'll know what that means. I'm just translating all of the language into my own terms. So then after that, it's super messy, but I'm just terrible at writing very neatly on this. The fatty acid profile of the longissimus thoracis muscle was derived and produced the following results. Now, I always say in all my videos, I never really read tables too closely. What I'd be trying to do is read all of the row labels and all of the column labels and get a sense of what it's showing me. So clearly I can see a bunch of different fatty acids, although we don't have the names. And then across here, we've got the three different diets. We're told that it is the milligrams of that fatty acid per 100 grams of the edible part of that meat. And then we've also got significance levels as well, looking at testing between energy, high energy versus protein, and the two different protein sources as well. There's a few notes down here, but it's all very disconnected, so I'm just going to kind of leave that off until I get to the questions. Then we've got the fatty acids are described by their carbon chain length, their degree of saturation, whether they're saturated, monounsaturated, or polyunsaturated. If you've done any organic chemistry, you might already be familiar with those acronyms. Otherwise, you might want to note those down. And whether they are omega-3 or omega-6 fatty acids, if at all. For example, the fatty acid denoted by C18:2 omega-6 is a polyunsaturated fatty acid with 18 carbons, 2 double bonds, and is an omega-6 fatty acid. So whenever they do this kind of thing, I've tried to put this one into my own question here to demonstrate this. Often you'll get presented with some new notation that you're not familiar with, but they will always explain it either explicitly or they will demonstrate it with an example. So that's what I'm doing here, is demonstrating it with an example. So what that really means is I could just write down a generic tool that says C, I'll do N, and then here I'm going to put like, I could just put A, B, C actually, not even bother with anything fancy. Just put A, comma, B, and then omega minus C. And then what I can do is in my notes, I might actually move this out to the side. Let's move this up here. What I would do on my paper is I would just write down against this carbon number. This is going to be double bond number. And then this here, that's a C, not a 6. C, this is going to be the omega number. And I might even just put down a note. It can only be 3 or 6. Those are the two. And there we go. Now I know how to read the table. You can see they're all here. Now I can make better sense of that. The next thing then is we've got, additionally, the atherogenic index, AI, is a measure of comprehensive fatty acid level and is a biomarker for coronary syndrome and metabolic syndrome. So again, I would make a note of that and I would just write AI. I wouldn't put equals to, but I'd put like an arrow. So it links to coronary, and I'm just going to put the keywords. So coronary and metabolic syndrome. There we go. And we've got a formula. It's got a standard log in it, where TG is triglyceride concentration in milligrams per 100 grams in blood 1 hour after consumption, and then pro-atherogenic fatty acids are going to be counted in these. HDL, high-density lipoprotein, concentration again in milligrams per 100 grams of blood 1 hour after consumption. These are anti-atherogenic, like that. Again, not really able to make a huge amount of sense of that. Just going to note that down, that maybe pro and anti-atherogenic is going to maybe be helpful to me in the STEM. Thrombogenic index TI is a quantifiable measure of the tendency to form blood clots in the vessels. That one makes a little bit more sense if you're familiar with thrombosis and the word itself. So TI basically going to be risk of blood clots. There we go. This is how I'd take notes, just kind of segmenting and breaking down, piecing it all apart. The fatty acid profile was also analysed for 3 different tissue types, and then we've got here LT, SF, and PF, and we can see these are different tissue types. We've got the muscle again, then we've got subcutaneous fat and perineal fat as well. All right, so, and then the 3 different saturated, monounsaturated, and polyunsaturated. Again, with graphs, I'm going to let the questions guide me. So with question 1, which of the following is true? So these are super annoying because it branches off into 4 different statements, and then we have to basically test each of them. So we've got high energy diets produce less saturated fat than high protein diets. Let's have a look at that. So we're looking for saturated fats. There's no mention of tissue type, so I know it's not related to the graph. I know it's going to go to the table. So if I go over here, high energy versus protein, and it says that it's going to produce less saturated fat. So I can find, there we are, there's saturated fat, and then I'm going to look at the high energy, produces 457, and we're going to compare that to, what was that? High energy diets. We're going to compare that to the high protein diets, and that's the other 2. So it does look to be higher, not less than, I believe is what the statement said. The other thing we have to look at is the significance. We're comparing high energy to protein, so we want to use this column, and we can see that's 2 stars. 2 stars is a P level of less than 0.01, so that means very, very significant, only a less than 1% chance of error or chance causing that relationship. So it says less, but the data says more, so that one is going to be out. Then we've got high protein diet significantly increases the risk of blood clots, so there's our keyword, compared to high energy. So remember, blood clots was linked to TI, larger TI means higher tendency to form blood clots, according to the statement. Where high energy increases TI versus high protein. So we look at this here, and we look at the TI values. So we can see high energy versus high protein, and clearly the high protein is actually lower, and it's significant again. So therefore, it's actually the wrong way around. High protein actually lowers the risk rather than increases the risk. So B is out. There was no significant impact on omega-6 fatty acid profiles based on the diet. So let's look at omega-6. And we look at omega-6, and we can see here 174, 188, and then 168. So there are some fluctuations, but you'll notice both high energy versus protein, there's no significance. And then also protein to protein source, there's also no significance. So although there are slight fluctuations, they're not significantly far away enough from each other to say that there's a relationship. And so that actually probably looks most true. There was no significant impact. So there we go. C is looking pretty good. Now, I would always rule out D as well. So protein source had the greatest impact on fatty acid profile. And so if we look to this here, that's comparing the protein source. If we look at the significance table for the comparing protein source, we can see there's only one significant change, and that was with C18. Everything else was not significant. So that is clearly a pretty false statement. The greatest impact, clearly not. So not significant at all. That's going to be out. Our answer then is left with C. So then question 2, which of the following conclusions can be made based on the above information? So the first one, again, we've got to test all of them. Meat quality is the cause of coronary syndrome. Now, first of all, that is already a very large claim to make. There's not a lot of causal relationship between these two given in the STEM. And we can see that, yes, meat quality might be increasing the risk of coronary syndrome because if we look at, for example, this table down here, fava bean versus soya bean, we can see the fava bean does increase the AI, which is directly related to the risk of coronary and metabolic syndrome. But in terms of comparing the source, there's no significance. So meat quality, overall, meat quality may be raising the AI value, but it doesn't necessarily directly cause it. It can increase the risk of it. So that one's not going to look too good. Fava bean fed bulls generally produce low coronary risk meat compared to soybean fed bulls. Let's have a look at that one. So coronary risk, still looking at AI. Fava bean lower than soybean? No, it's clearly slightly higher. So that's also out. Also, there was a no significance level, so even that alone, you couldn't make any conclusions. Then we've got saturated fatty acids are a likely cause for increased risk of coronary syndrome and blood clots. Now, this is a possibility. So we look at that. We look to saturated fatty acids, and we can see, here it is here. We can see that it's highest in the high energy diet, and what happened to those two figures? They are higher than their protein counterparts, right? If we track that again and we look at the lowest value, which was in soybean, we can see we get the lowest risk. And then in the kind of middle ground, the 365 and the fava bean, we've got some middle ground risk. So there does seem to be some linear relationship there. So saturated fatty acids are a likely cause. Given that they're tracking with the AI and TI values, this is looking pretty good. We'll go by process of elimination and see what D is doing. Then we've got high energy diets generally lead to lower amounts of monounsaturated fatty acids of carbon chain length n equals 20. So let me read that again because I've lost myself in my own question. High energy diets generally lead to lower amounts of monounsaturated fatty acids. Let's have a look at that. So for n equals 20, there's these three here. Now we're looking at high energy diets, and I've lost it already. My memory's shocking. Generally leads to lower amounts of monounsaturated. Okay, so monounsaturated is this one here because it's got the 1 against it, the number of double bonds in it. And high energy leads to a lower amount. So if we compare that to the others, it looks okay, but you can see that this is 1.66, and it is lower than the other forms. However, it's not significant again. So it's lower, but it's not significantly lower. So although that seems okay, it's not low enough to be significant to actually suggest there's a relationship. So that's ruled out. So C is going to be our answer. Then question 3, we've got a study into human consumption of red meat produced by these diet-reared bulls was conducted in which participants consumed 200 grams of the meat and their blood was then drawn, and after 1 hour since consumption, it would be, and analysed, I missed a word, and analysed. I'll fix that before this video goes up. And analysed after 1 hour since consumption. It would be expected that the triglyceride concentration in the blood of a healthy individual who had consumed the meat produced by the fava bean-fed bull would have approximately what? Now, this is getting into the formula here, right? So, we can see that the AI value is based on the fava bean-fed bull, and that is 0.54 from the table. So what we're going to do is we're going to plug that into the equation and look at the relative ratio of triglycerides to high-density lipoprotein, because that's what all the answers are doing as well. That's kind of our hint. So if we've got 0.54 is equal to log 10 of triglyceride to HDL, then we can rearrange this and we can say the brackets, Tg over HDL, is equal to the base to the power of the answer. And then we've got to equate this. Now, you're not expected to know how to do 10 to the power of 0.5 in your head, but what you can do is you can go, well, 10 to the power of 0 is 1, 10 to the power of 1 is 10. So anything in between is going to be anything in between. So between 1 and 10 times, right? So Tg over HDL is equal to something between 1 to 10. I'm just going to write that for now and be lazy about it. So then we're comparing triglyceride to HDL. So if I multiply the HDL over, I can now get 1 to 10 times HDL. So there's my factor, anything between 1 and 10. So if we do this, then we have to go, all right, so what is 10 to the power of 0.54? So you could write that as 10 to the power of, it's around about half, which is then the square root of 10. It's probably a little bit too technical. I might adjust this question. And then you can go, okay, so what's then the square root of 10? You can go, well, the square root of 4 is 2, and the square root of 9 is 3, the square root of 16 is 4, so the square root of 10 sits pretty close to 9, so it's going to be maybe 3.1 or something like that. So there we go. So the number we're looking for is about 3.1 times HDL. Now, keep in mind, this is based on the concentrations. So although they did eat 200 grams of the meat, yes, the concentrations would be double, but we're looking at the factor of change between the concentrations, not the absolute amount of the fatty acid. So the trick to it is, although it looks like you would double it and go to 6, it is still just it's 3 times the triglyceride concentration, because it's just a ratio of concentrations, which is what the formula actually gives us. All right, let's see that. Oh, one question. Okay, then question 4, we've got figure 1 shows which of the following. So we have to make conclusions. So again, a bit of an annoying question. We've got fatty acid profile, the 3 different types. I'd probably just test all of the options. It's quite a slow question. As the degree of unsaturation increases, so it becomes more unsaturated, the lipid content of the muscle decreases. Let's have a look at that. So as we increase the unsaturation, we go to the right, then the lipid content of the muscle decreases. So if we look at this, these are all percentages on this side. So if you looked at, for example, the muscle group, which is the black bars, if you add up all of their values, they're going to add to 100% because it's percentage of all of the fatty acids, not percentage of the muscle tissue or of the tissue itself. So what that means is we can't ever actually know whether or not the fatty acid content, say in grams, is actually going up or down based on this. So therefore, that one is out from that figure. Now notice it says figure 1 shows. Sure, you could maybe go through and analyze all of the numbers in the first table, but you're going to end up killing a lot of time because it doesn't actually care about that. It's just, what does figure 1 tell us? What conclusions can we make from it? B, the monounsaturated fatty acids are most localized to certain tissues. So let's look at monounsaturated. And we can see that they seem to have equal proportions across the 3 tissues, which means they are not really localized. They're relatively evenly spread out and evenly distributed, so that one's no good. Polyunsaturated fatty acids make up approximately 1/3 of the lipid profile contribution in perineal fat as monounsaturated fatty acids. That's a lot to take in. So we're looking at perineal fat. I usually, with these ones, I just kind of try to remember all the bits and pieces first. Polyunsaturated versus monounsaturated. So then it was 1/3. So if I look at that, I run that across, and I can see that section there, yeah, it's about 1/3, right? 1/3 of that in the monounsaturated fats in the same tissue. So that's looking pretty true. And then finally, approximately 45% of all saturated fats come from the longissimus thoracis. So if we look at that, we can see 45% for the saturated, but that is 45% of the fatty acids in that, of the fatty acids in the muscle tissue are saturated. It's not 45% of all fatty acids. So that one is false as well. Question 5, if figure 1 was collected from data from bulls fed on the FB diet, what would you expect to see of the same graph analyzing results collected from bulls fed on the HE diet? So compared to FB, what would HE do? And from the answers, we're looking at the proportions of the 3 different fatty acids. So that means we have to go way back to the dietary information, and then we look at these 3 here. So let's maybe clear off some of this scribbling and look at what's happening. So we're looking through here, and we can see that the saturated fatty acids compared to the FB, we can see the saturated increases. The monounsaturated didn't seem to change all that much, and neither did this one here, like that. So let's jump back over. So the proportion of saturated fats would increase because if the other 2 are not really changing, but the total mass of fatty acids is going up because they're all going up a little bit, then what that means is that the 2 that stay stable, the monounsaturated and the polyunsaturated, will now make up a smaller portion of this larger total of mass of fatty acids. So what that would mean is the SFA would increase, and although the other 2 seem to be relatively stable, the proportion that they make up of this larger mass of fatty acids is actually going to decrease. And so therefore, it's going to be A, like that. That's what we would see. All right, so now let's go through this one. So this is a stem that doesn't actually have a stem to it. It's just a mix of different organic pathways. They might say something like, consider the following reaction pathways, and you have nothing else to go off of. So we just have to basically adapt to what we're being shown and use chemical pathway analysis and keep adjusting to new formats each time. So what is the byproduct of the above reaction? So this is the product. The byproduct is the extra chemicals that aren't accounted for. So remember, these are just, whenever it's under the arrow, these are just used as applying the correct conditions. They're not actually going to interact or react. So therefore, that's already not looking very good. What I would do is I would look at what's actually happening to the compound. So if I try to trace and track where my reagents went, I can see that this acetone, I believe it is, has glued on here. And it seems to have glued through its 3rd carbon onto this carbon right here. So what would happen in that process? There would have been 2 hydrogens normally attached here, and there would have been a couple of hydrogens here. Yet when it's glued, there would only be 1 hydrogen that is able to actually bond there. So based on that, what would be the byproduct of this? We've got 3 hydrogens that are not accounted for, like this. And so that would mean that we would end up with H2 gas, right? Now, in terms of the ratios are slightly off. So correct me if I'm wrong here. I might be slightly off on that. I think when I wrote it, I had the idea that there would be 2. And so therefore, that would lead you to this as the final answer. Then we've got question 7, same thing. What is the byproduct of this reaction? So they don't necessarily try to get you to stretch too much, but they do get you to adapt to new scenarios each time. So now we've got to look at this one. We've got palladium and all this other stuff going on. So what's happening to it? We can see this big structure here has glued on just here, and it looks like the iodine end has disappeared and it seems to have glued itself just here. So that means we're losing the iodine and it's gluing itself on here. Everything else seems to be accounted for and nothing else has changed in the rest of the molecule. So what that means is there would only be iodine being freed up. However, keep in mind this carbon here, again, let's look for the hydrogens. There would have been 2 hydrogens. Now there's only 1. So there's another hydrogen that's missing and an iodine, and they can glue together, form iodic acid. There we go. So you can see the skill, once you kind of click onto it, it'll keep using that same kind of skill in different contexts. So then question 8, now we have which of the following is true. We're looking at this. I would read the answers here and get a sense of what I'm looking for. Compound 21 has more or less stereoisomers than compound 23. So basically, stereoisomers, you will have 2 to the power of n stereoisomers, right? Where n is the number of chiral centers. And this is, you can kind of use a bit of maths. You can use like combinatorics to explain this. Basically, my legs are going to sleep. Oh my God. Ugh. Cross-legged, I should never do that. Oh, I can't feel my legs. Okay, there we go. It still hurts like hell. It's kind of like combinatorics. For every chiral carbon, you have an R and an S geometry to it. So there's always 2 different versions every time. And so therefore, if you've got 2 chiral carbons, well, then you'd have 2 times 2 different combinations. So in this one, we just have to count the chiral carbons. So we're looking for the carbons that have 4 different attachments or 4 different attachments to it. And they all have to be uniquely different from each other. So all of this, there's not going to be one. They've all got double bonds to them. If we start going, we've got 1 here, right? So we've got hydrogen, this kind of phenylphthalein attached, I believe is what that's a shortening for. This branch and this gigantic branch. They're all different. So we've got 1 chiral center there. Then we have no other chiral centers, right? Because this would have 2 hydrogens and this has 2 methyl groups. If we look at compound 23, all of this is unchanged, so we're not going to see any difference there. And we now have another chiral center here. So what that means is that carbon or compound 21 would have 2 to the power of 1, compound 23 would have 2 to the power of 2. That is 2 versus 4. So that means compound 21 will have 2 fewer than compound 23. And there's B. Cool. All right, so then number 9. So the byproduct again, the byproduct of the above reaction is what? So we're going to use that exact same skill. So this one's a little bit trickier. So in this one, what we have to look at now is, again, what's changing. All of this is not changing. This doesn't seem to be changing. It's all there. What we do have, though, is a ring forming. So we have to think about where the carbons are. So there's a carbon here and a carbon here. So if we bend this carbon down and then glue it onto this carbon, we will get this shape. So that's accounted for. The next thing is then, that means that there would be nothing poking out, because remember, this is not a carbon, we've just got a hydrogen attached. So that's okay. The next thing then is what else happened? Then we added this compound onto it. So if we do that, it looks like the nitrogen's disappeared and we've glued it onto this position here. So now we know the byproduct, we do have nitrogen coming out. Then we have to track our hydrogens and see what's happening there. So on this one, there would have been no extra hydrogens on either of these carbons because it's triple bonded. And then this hydrogen, you would think, wait, that's gone. But if you look to it, if you look at that, then there will be hydrogen missing because here, this carbon has already got its 4 bonds. It doesn't have any space for another hydrogen. So there's also a hydrogen that's disappeared as well. And so putting that together, what that means is that the reaction, in terms of what you could make, is the only one that is reasonable is nitrogen gas. This one would not have anything to go with. Now you might start to think, okay, this one as well, but look at the ratios. You can see the ratio of hydrogen to nitrogen is 1 to 2, and the ratio here is 3 to 1. So even if you keep multiplying this, you'll never be able to make an even number of ammonia in that case. That is why ammonia will not actually be the answer in this one. So it just says the byproduct of it. So implying 1, the only one that's reasonable is this one here. Now, truthfully, you could argue I might actually change that to a byproduct, because the other argument you could make is, well, what if you doubled it? Then you'd have 2 hydrogens and you can make H2 gas. So if you were thinking that, I'll say give yourself the mark on that one. It's a bit of an error on my part. I'll change that to a byproduct though. We'll see how we go. Cool. And there we go. That's pretty much it. So 9 questions there. I'll keep trying to bang these out as frequently as possible. The thing that I think I want people to take from these videos is that, yes, there is some science in section 3. Yes, you do need to be familiar with some scientific principles, but very little. So most of what we were applying in the first one is actually data analysis more than anything, and a bit of maths along the way with the logs. But that being said, if you didn't know anything about double bonds or fatty acids and their structures and that kind of thing, then it would be a very, very tough read. You could potentially still get through it, but you'd be limiting your ability to work quickly if you're relying heavily on what the STEM is telling you. So although we interpret these very literally on the day, it's important to be familiar with the basic scientific concepts and the kind of language of the science. You do not need to know about fava beans and soya beans. You don't need to know anything specific about the muscle that was mentioned. Likewise in the organic chemistry, I couldn't tell you what these reactions actually are, right? I have no idea. The point of it is to take the context out of it and actually look at it as a puzzle every time, and look at the generic skills that will work regardless of what they're actually throwing at you. So hopefully that was helpful. Yeah, I'll leave that one there pretty much. I'll try to keep these to about 30 minutes. So I'll try to edit this one down and see how we go. Anyway, hopefully did well on those 9 questions, and I'll keep banging out more of these and we'll keep going. All right, I'll see you in the next video.